We finally got all the tools we need to start sketching curves using our calculus. So I'm going to just briefly go through all the things that we're going to do, all the stuff we have to find before we actually sketch our curve, and then I'll go through a few examples. So a lot of the basic stuff that we used to find is still going to apply, right? Like x-intercepts, we're going to want to know where it crosses the x-axis. Y-intercepts, we can use symmetry, which I didn't put on the list, but symmetry is good. Sometimes we're not necessarily going to need it if we get enough information to start with, but we could use symmetry. I'm just going to type that in there. And we would find symmetry by plugging in negative x for all x's. Okay, so kind of these three things, the x, y intercepts, and symmetry are stuff that we learned a long time ago. Y-intercepts, you put 0 in for x, that'll tell you where it crosses the y-axis. We're going to find vertical asymptotes, so that's where the function ends up dividing by 0, so which x values will give us an undefined value that way. Horizontal asymptotes, which is what the last lesson was on, so using our limits as we approach infinity and negative infinity. End behavior, kind of the same thing. Our relative mins and maxes, which we get from our critical numbers. Our concavity, which we get from our points of inflection. And our second derivative test. And then I guess we could fit slant asymptotes in here too. Okay, they kind of fit in with our other asymptotes. Okay, so we're going to use all this stuff to sketch a pretty accurate graph. So here's my first example. We'll start off kind of simple. This is just a polynomial function, and then we'll kind of get into some more complex things. So let's start with the real basics. We need x-intercepts. Okay, so I need to know when this thing equals 0. So there's a few ways to solve that. I could try factoring. I could use a quadratic formula on this one. Or I could complete the square and then set that completed square equal to 0. Let's see. This one's going to be hard to factor the way it is now. But if I can clear the fraction, it might make it a little easier. So if I've got 3x to the 4 minus 6x squared plus 5/3, and I want to know when this equals 0, I'm going to multiply each side by 3 to get rid of this fraction. So I have 9x to the 4 minus 18x squared plus 5 equals 0. Let's see if this will factor. So in order to get 9, I could do 3 and 3. In order to get 5, I need 5 and 1. And my signs are both going to be negative. Okay, and does this work? This would give me negative 15 minus 3 is negative 18. So it does factor. And actually, I should have squareds here. So I've got two factors that are multiplying to be 0, so that means one of these two factors has to be 0. So if I solve this, I'm going to get 1/3 x squared equals 1/3 square root of that. So I'm going to get x equals plus or minus the square root of 1/3. If we simplify and rationalize, I'm going to have plus or minus square root of 3 over 3. This one I'm going to get plus or minus the square root of 5/3. Again, if I rationalize here, I'd have the square root of 5 over the square root of 3. So I need to multiply top and bottom by the square root of 3. So I get the square root of 15 over 3. Okay, these are all my x-intercepts, so I've got 4 of them. I'm just going to bring up my calculator quick here. Because we're going to want to get some decimals so we can actually put the points on our graph. So let's see what the square root of 3 over 3 is. Plus or minus 5.78, or 5.77, so we'll just do 5.8. Plus or minus 0.58. And the square root of 15 over 3 is plus or minus 1.3, we'll say. So those are all my x-intercepts, so I can put those on the graph. So 0.58, I'm going to make this graph a little bigger here. And we'll just put it down here so that we can just keep adding to it as we go. So I got plus or minus 0.58. So, you know, right around here. And then we got plus or minus 1.3. Okay, so those are all our x-intercepts. Next we need our y-intercept. We can get that by putting 0 in. So if I put 0 in for x, I'm going to get 5/3. So my y-intercept is at 5/3. So I can put that on there. That'd be 1 2/3. Any asymptotes? This one's not going to have any because we're not dividing by a variable. So now let's find our critical points. Okay, so I'm going to take the first derivative of this and then set it equal to 0. So the first derivative would be 12x cubed minus 12x. Set this equal to 0. I can take an x out. I can actually take a 12x out. And then I'd have x squared minus 1, which factors into x plus 1, x minus 1. Okay, and if I want this to be 0, I'm going to set each factor equal to 0. So this one would give me 0, this one will give me -1, and this one will give me 1. So those are my critical points. 0, -1, and 1. So that's where I'm going to have relative mins or maxes. So I'm going to plug those into my original function. So I've already plugged 0 in, so I know this is going to be a min or a max. If I put -1 in here, I'm going to get 3 plus 6, which is 9, plus 5/3 is 10 2/3. So -1, I'm at 10 2/3. So here's 10 2/3. When I put in +1, I'm going to have 3 minus 6, which is -3 plus 5/3. Actually, I did that one wrong. I did a -1 wrong. Because this is squared, not cubed. So I'm going to have 3 minus 6, which is -3 plus 5/3. -3 plus 5/3. So -1 1/3. And that's going to be my answer for both of them, actually. So -1 is at -1 1/3. And 1 is at -1 1/3. And I can kind of see from my graph that those are going to be relative mins because I'm crossing zeros around there. So I'm starting to get a shape here. My end behavior, actually let's do points of inflection. So if I take the derivative of my first derivative, I would have 36x squared minus 12. I need to know when that equals 0. I'm going to divide by 12 to get 3x minus 1. Okay, so my point of inflection is going to be when x equals... Oh wait, I had a squared here. So plus or minus the square root of 1/3, which is actually... that was my 0.2. So these zeros here are actually points of inflection. So it's going to be changing. Since this is a max, it's going to be concave down here. It's going to change to concave up right at that point. Okay, and now I just need end behavior. So if I look here, I know both ends are going to be going up. So now I can kind of draw my graph. So here's my point of inflection. Okay, so it's going to go concave down, switch there and become concave up, and then it's going to shoot up to positive infinity. Here it was concave down, it's changing to concave up. It's going to stay concave up and go up that way. So that's my first graph. I've got it graphed out on a graphing program here to kind of compare what I did to what the graphing program did, and you can kind of see it's exactly the same. I've got the same y-intercept, I've got all the x-intercepts, I've got the same min and maxes, and I've got the same end behavior. Let's go on to one that's a little bit more challenging. So for this one, I'm going to do all the same things. Let's make my graph bigger again and move it down to the bottom. Give myself some room to work here. So same things. I need x-intercepts. So I'm going to set this thing equal to 0. The only time it's going to be equal to 0 is when x is 0. So x-intercept is going to be 0, 0. My y-intercept, if I put 0 in, I'm going to get 0 over negative 4, which is 0. So my y-intercept is also 0, 0. Vertical asymptotes. Okay, for vertical asymptotes, I need to know when the bottom is 0. The bottom factors into x plus 2 and x minus 2. Okay, so those give me vertical asymptotes at when x equals plus or minus 2. This one's actually going to have a slant asymptote too, because my power on the top is exactly 1 higher. So I'm going to do my long division. So I'm going to multiply by x. That gives me x cubed minus 4x. Change my signs. I get 4x. And I get a remainder of 4x over x squared minus 4. And when I take the limit of this thing, so when I'm putting in large numbers, this is going to go to 0. So really my slant asymptote is just x. So y equals x. That's my slant asymptote. Let's see. What else do we need? End behavior. My end behavior, okay, it's going to approach infinity, so that's kind of the same as my slant asymptote. I need critical points. So I need the first derivative. So this is going to be quotient rule, so I'm going to take bottom times derivative of the top minus top times derivative of the bottom over the bottom squared. Do some simplifying here. I'm going to have 3x to the fourth minus 12x squared minus 2x to the fourth. So I'm going to have x to the fourth minus 12x squared. Okay. So I already know there's vertical asymptotes at plus or minus 2, and those would be critical points too, but since they don't exist on the graph, we're not going to have to worry about those. I really just need to worry about when this top equals 0. So I could factor out an x squared. Oops, that should be 2 now. Okay, so that's going to give me a critical point at 0. So 0, 0 is also relative min-max. One or the other. Set this equal to 0, this factor, and I'm going to get plus or minus a square root of 12, which is 2 squared of 3. So plus or minus 3.5, okay, give or take, just a little bit less than 3.5. Those will be other critical points. So when I'm at 3.46, if I plug that in here, that'll tell me exactly where my min-max is. So we'll just store that as x, and then we'll do x cubed divided by x squared minus 4. Okay, so that completes the point for one of my min-maxes. If I'm at the negative version of it, let's times it by -1 and then restore it as x. And then just go back a couple entries to where I typed in my equation. Just to enter again, and now I get, okay, it's just the opposite. So I've got some min-maxes here. Those are my critical points. I need points of inflection, so I'm going to take the derivative of this thing. Okay, to get my second derivative here. Let's see. So take bottom times derivative of the top, which would be 4x cubed minus 24x minus, let's move this over, minus top times derivative of the bottom, which would be chain rule, so I'm going to drop the 2, lower the power by 1, times derivative of the inside part, which is 2x, all over the bottom squared. So that's going to bring it to the 4th power here. Let's do some simplifying. Let's see. I'm going to pull out an x squared minus 4. Okay, and then I can pull a 4 out of this, and this is a 4, so I can actually pull a 4x out of here. So if I pull 4x out of this term and this term, okay, that's taking care of these. This then turns into x squared minus 6. So far I've pulled out an x squared minus 4 from here, which leaves one of them. times that x squared minus 6 minus, let's see, I pulled this one out, so that's not there anymore. So really I've just got minus x to the fourth, and then I'll turn this into a plus 12x squared. Let's multiply this out to get x to the fourth minus 10x squared plus 24 minus x to the fourth will cancel this, plus 12x squared turns this into 2x squared plus 24. Okay, so that worked out pretty well. Then I've got this still sitting outside. So this equals 0. So my critical points are going to be at 0. This one's going to give me plus or minus 2, but those don't exist again, so we don't have to worry about those. I guess I'll write them down anyways. And then this one, if I set this equal to 0, I'm going to divide by 2, and this is 12. This is going to turn out to be imaginary, right? Because x squared plus 12, I'd subtract the 12 over, and I'm square rooting a negative 12. So these give me imaginary inflection points, so I don't need to worry about those. So these are my inflection points. All right, so let's start plugging everything we've got. I've got a point at 0, 0, okay, which is a min-max and my x-intercept and my y-intercept. I've got critical points at 3.46, comma 5 point, roughly 2. Okay, and then same thing on the negative side, negative 1, 2. Okay. Oh, this should be negative though. 1, 2, 3, 4, 5, right there. Okay, and then let's see, we've got our vertical asymptotes at plus or minus 2. I've got a slant asymptote here. That's going to affect my end behavior. Okay. Remember that slant asymptote isn't really going to affect the inside part here. Let's see. I've got point of inflection here at 0, 0. So that means it's changing. Okay, it's either so I need to do a test to see if it's concave up or concave down on the left here. So let's plug negative 1 into my simplified second derivative here. If I put negative 1 in here, this is going to be negative. This will be negative 3, so negative negative is positive, times this will be positive. So it comes out positive, so it's concave up, which means over here needs to be concave up, swooping up. So I know that it's going this way, and then the right side is going to be coming this way. Okay, so I'm approaching my asymptote that way. Okay, here it's changing from concave up, which would be like this. It's becoming concave down and approaching the asymptote. I've got this point here, which is a relative min or max, and since I know I have to approach this slant asymptote and this asymptote, we could use our first derivative test to test to see if it's a min or max, but it's going to be increasing on this side and decreasing on this side. So approaching my slant asymptote, approaching my vertical asymptote. Here, this one's going to approach my slant. And this. Okay. Another thing that lets me know that it's doing this is I know it's a min or max because it's critical point. And if I tried to draw it, approaching this asymptote this way, and knowing that it needs to approach this, it would kind of be doing this weird thing, which isn't very likely, but I really should use my first derivative test to check it out. So let's do that real quick. Let's put this point back in there. So my first derivative is here. I'm going to test a point like, I can do 3. If I put 3 in here, I'm going to get positive minus some number, which is going to be smaller, because 3 to the 4th is much bigger than, well, 3 to the 4th is 81 minus 12 times 9. Which, let's see, so that is negative on top. The bottom here is going to be positive, so negative over positive is negative. So it is decreasing here, and then switching and increasing. Okay, and just by symmetry, we're going to have this one's doing this. Okay, now let's look at a graph of this one. Okay, pretty close to what I have. Okay, same asymptotes. Got the same behavior here. Okay, so I think I'll leave it there. I do have one more example, but I think I'll put that as another video.